Hello everyone, welcome to our webinar. We're just waiting for a few more attendees to join and we'll start shortly.
Would you like to chat with the Alexis about social bot?
Stop. I cannot answer. Camera.
Hello everyone, welcome to our webinar. We're just waiting for a few more attendees to join and we'll begin shortly. Hello everyone and welcome to our webinar presented by Veolia Water Technologies and brought to you by Coal Publishing and Treatment Plant Operator Magazine, also known as TPO. My name is Anthony Drew and I'm the digital editor for TPO. In this webinar, titled Advanced Control Techniques Enhance Biological Phosphorus Removal and Save Significant Operating Costs, you'll hear about a Danish wastewater treatment facility that was faced with increasing chemical costs to reduce phosphorus levels in its discharge. Its existing real-time process control approach left much room for improvement, which is why the facility turned to AQUAVISTA Plant by Veolia Water Technologies. The new system allows the facility to enhance biological phosphorus removal without dedicated anaerobic selector zones, resulting in substantial savings and other benefits. During the webinar, you'll be able to submit questions. In your control panel, you'll see a series of drop-down menus, including one titled Questions, and that's where you'll submit. At the end of the presentation, our panelists will answer those as time permits. Afterward, they'll send responses to all the questions asked by those attending the webinar. Now I'd like to introduce our panelists. First, we have Mark Drake, Product Manager for Veolia Water Technologies. Mark has been a water professional for over 20 years. He obtained his BS in Chemical Engineering from Iowa State University. Mark has been part of the Veolia team since 2010 as a product manager for biological products and as product champion for the AQUAVISTA line of digital solutions. Mark is also active in the North Carolina AWWA-WEA, where he currently serves as both Schools Council Chair and as the Chair of the Wastewater Operators School Committee. He also teaches several classes for treatment facility operators. Also joining us today will be Larsen, Project Engineer at Kruger in charge of business development and implementations of AQUAVISTA Plant globally. He is a Cornell University chemical engineering graduate who has been working for Veolia for 4 years. And with that, I'll turn the program over to Mark Drake.
All right, thank you very much. Welcome everyone. Look forward to a great webinar today. First, I'm just going to give a quick background here on Veolia Water Technologies. Many of you may be familiar with us. But we are the division within Veolia that focuses on providing technologies and services into water and wastewater markets. We have many different technologies that span from preliminary treatment to biological treatment, to tertiary treatment, and then some. We deliver those to our customers, both municipal and industrial, and also a wide range of services that go along with those technologies. The focus today is going to be on a particular digital service that we offer, and with a highlight of a facility in Denmark that is implemented for some time, one of those digital solutions, digital services, to help them in a number of ways. First, we'll talk just very briefly about some common wastewater challenges. And then we'll drill in a little bit on the facility and with some background of the plant that we're mostly going to focus on today. We'll talk a little bit about the actual treatment technology that they employ, and then we'll really move into a discussion on the digital solution that they have implemented, and talk about the results that they've seen at that facility. So, we have many challenges that our treatment facilities face around the world. Here in the US, in Europe, in Asia Pacific regions, we all have to deal with increasing loads, meeting compliance set forth by our national and local, state and local governments. And we all have operations costs that we are trying to reduce. Those are some direct challenges that we deal with. We have indirect challenges that we deal with, and these have become more and more prominent every day, and that is changes within our workforce, turnover among our operations staff, the need to better train operators and to give them better tools to keep our facilities running smoothly. And a big part of that is taking data, and we have more data today than we've ever had before. We have better data, more reliable data, and being able to take that and get the most out of it, make the most use from it. That manifests itself in what we see our customers asking for, and that is how do they leverage that data and how do they get a return on investment on it. And we see it all around us in other industries, this digital transformation, and how do we capitalize on that to make the lives of our treatment facility operators and managers, make their lives better, to improve performance, improve compliance, save money, etc. So, the way that we do that is, we focus on things that reduce energy costs, reduce chemical costs, and make manpower more efficient. We focus on solutions in the digital world that will allow us to improve hydraulic capacity, and we see that in a number of ways. That is managing things better in collection systems to reduce overflows and reduce bypasses, and to get more capacity, more flow through our facilities, and doing so with hopefully avoiding significant capital expenditures, i.e. putting in a bunch of concrete. Hand in hand with that oftentimes is a need to increase biological capacity. With the right digital solutions, we can affect change in that area as well, allowing facilities to get a higher biological load, get more BOD, more ammonia through that existing infrastructure, and do so with better effluent quality and reduced capital costs, reduced OPEX, and also avoid CAPEX. Again, avoid adding concrete where we don't necessarily need to add concrete. And we can affect change by increasing capacity in sewer systems. Again, that comes down to how we manage flows within the sewer system. And that isn't so much the focus today, but that is an area that we can certainly have an impact. So I want to talk now a little bit about the facility that we are going to focus on today. Louis will correct me, I'm sure, if I make any mispronunciations, which I'm likely to do. I do that with English language plenty of times, so Danish is it's going to happen. So the facility we're going to see a little bit of information on today is in the Krueger region of Denmark. It's an area just south of Copenhagen. You see a nice picture there of the harbor in that region. It's around 40,000 population in the main municipal area. The surrounding region that makes up the what feeds to the treatment plant is about 65,000 people. The facility that we're going to talk about today is served by Klar Forsyning utility. I'm sure I just got that wrong, but in terms of pronunciation, it actually the treatment plant that they operate serves 4 municipalities, Kruger and 3 others. Altogether, the capacity of the plant is about 5.3 MGD, and population equivalence is around 100,000. Now, wastewater treatment in Denmark, they have a rich history in wastewater treatment. The Kruger business that Louis works for, I think, was started up around 1903 in Denmark, and has served Denmark and Europe and beyond for over 100 years now. And so they have a very rich history in treatment. And in Denmark specifically, they really began implementing nutrient regulations in the 1960s. You can see here how they've had an impact on nutrient emissions with the implementation of nutrient standards back in the late 1960s. Many of those facilities, including the one we're talking about today, utilize oxidation ditch technologies. And I wanted to give just a brief introduction into a specific type of oxidation ditch technology that's employed a lot there. There are a number of facilities of this type in the United States as well. And that is a phased isolation ditch technology, whereby you operate the system in a way, it has a control strategy that allows the full volume of each ditch or reactor. There are configurations that do not utilize the racetrack style ditch, but utilize more conventional rectangular concrete tanks. Allows it to operate that entire volume either aerobically or anoxically, and also allows the system to flow in series through the main reactors, or in parallel, or just through one of the reactors, allowing another reactor to be fully isolated. Here we see just a simple schematic of that process in oxidation ditches, and on the right you see a system that is currently under construction in Kansas that is 2 trains of the technology, train 1, train 2. These are some sledge holding tanks. This is post-anoxic zones. And that technology is about 4 MGD plant in Kansas that's under construction now. And that will feature the AQUAVISTA Plant digital technologies that we're going to focus in on here today. A way to think about that technology is it sort of falls between typical continuous flow processes, where you have continuous flow through the system, and there's no phasing generally of the aeration. You have dedicated zones for an anoxic zone, a dedicated zone for an aerobic zone. You have a secondary clarifier, obviously, for dedicated settling. We compare and contrast that with an SBR type system, which is a batch flow and phased aeration. Some of those systems do have continuous flow in, but they all will incorporate settling in the reactors, and so it's intermittent discharge. And those will go through a phasing of the aeration to achieve aerobic and anoxic conditions in the full volume. With the technology that we're talking about, the oxidation ditches, they have the separate mixing and aeration, so they do phase the aeration, but they are not generally settling in those reactors. They utilize conventional secondary clarifiers, and so they are continuous flow processes. But we do change how the flow goes through, so we can really manipulate, and it brings a lot of flexibility to the system to deal with variable influent and variable conditions, and get the right reactor environment in the right place at the right time, to take as much advantage of influent carbon as we can, and to really drive nutrient values down to the lowest levels that we can. So let's drill in here to the AQUAVISTA plant in Denmark. That is a 5.3 MGD ditch system, as I noted. They have primary clarification, and their limits in place are for 8 total nitrogen and 1.5 milligrams per liter of total phosphorus. So not super stringent on the phosphorus, but there is that limit in place. It is also a facility, you can see it's sort of on the coast there, that has, this area in Denmark has proven to be very susceptible to wet weather events. The image on the right is from a study that was done a number of years ago, really looking at sea level rise and impacts in the community. They have undoubtedly experienced more and more an increasing level of I&I over the years, as they are seeing sea level rise to some extent. So that part of it is calling for some solutions that help them manage their wet weather better, and we'll talk a little bit about that. From the phosphorus perspective, you can see in the picture the plant doesn't have anaerobic selectors. Initially the plant achieved very little enhanced biological phosphorus removal. And in fact, they actually had implemented some advanced real-time controls on their own a number of years ago, and were operating the plant that way. And with that, we're really not able to achieve any significant BIOP. And so what they needed to do in terms of meeting their effluent phosphorus, they simply had to do chemically. So all of these things together, combine to create room for a lot of optimization. And there are different ways to approach that optimization. The facility, again, they tried different meters to help with energy efficiency. They tried that real-time control. Didn't see a whole lot of improvement with that. With the sea level rise, they've experienced clarifier washout events. So, some of the other solutions, the things that you might, think of off the top of your head, add some additional secondary clarifier volume, or add anaerobic selectors, or add additional retention basins out in the collection system to equalize wet weather flows, and go that route to minimize sewer system overflows, and better manage flows as they come into the plant. And from a total nitrogen perspective, add potentially additional treatment volume. So, all of those types of solutions, they come at a high cost. They come at a high capital cost, don't necessarily address energy efficiency or excess chemical costs. Those are pretty significant projects to undertake. So the question was, is there a way to approach all of those issues with a digital solution and have an effect on energy efficiency, on chemical consumption, on biological phosphorus removal, on management of wet weather flows, and do so without putting in all of this concrete and rebar and additional infrastructure. And it turns out there absolutely is. We have implemented what we call our AQUAVISTA Plant, which we view as optimization as a service. And with that, I want to turn it over to Louis to talk a little bit in detail about what we offer with AQUAVISTA Plant and what it is.
Thanks a lot, Mark. Great introduction. Thought you also did well on your Danish.
Thank you.
So yes, AQUAVISTA Plant Optimization as a Service. What I mean by that is, this is a tool created by Veolia Water Technologies and Kruger and developed over the years. So this is a digital tool that really aims at answering all the problems and issues that Mark highlighted earlier. So it's both something that can deliver optimization for wastewater treatment on OPEX, but also on CAPEX savings. And as you see on the half wheel you have on the right side of the screen, that you can choose to have the product provide the service with different aims. So it can be regarding the water quality in the effluent. It can be regarding the chemical dosing. So pretty much as Krueger as you have it here, where they were dosing quite a bit of chemicals to reach their P consent. The biological capacity and the energy savings that Mark talked about. So the system and the platform is built in a way that it can adapt to any kind of needs. So that supports this modular offer. So there is embedded into the platform 60 different algorithms, more than 60 actually at the moment, that have been developed over time. So the first ones were thought of back in the early 90s. And since then, they've only been getting better and new and more innovative. And we've kept on building on it to provide this optimization. And any plant can identify their problems and then put together the right mix and match of algorithms to provide the best ROI, basically, on a project to solve this issue. So AQUAVISTA Plant is a digital product, as Mark said, so it works as a software as a service. You guys are probably all very aware of it. It's kind of like your Netflix account. You subscribe, you get the service, and if you're happy, you stay subscribed. If not, you unsubscribe. So it's a very user-friendly tool and way of looking at optimization for wastewater treatment. It's based on a state-of-the-art digital twin technology, so it's really creating your whole plant up in the cloud to best provide real-time optimization delivered from the cloud to your asset. And it works, so as we said, in real time, so everything is updated and calculated and rerun within a 2-minute time frame. And all the data that's put together in the algorithms is running 24/7, 365 to always keep track of how the process is going. And each month there are releases on the platform that can range from anything in better algorithms to a more user-friendly experience. It can be new user interfaces, new possibilities of settings for your algorithms, what have you, but it's a moving product.
Thank you, Louis. So with this digital service, so, as you mentioned, there are more than 60 individual algorithms, and we have facilities where we've applied, say, just 1 or 2 that are really kind of targeted on one specific technology or one specific product, to implementing a dozen or more of the algorithms that are all working together to optimize across a range of unit operations in a plant and out into the collection system. It all relies on IoT, advanced analytics. As Louis said, we have these algorithms that have been developed that are running this digital twin in the cloud. We work with through Amazon Web Service to deliver this to the facilities, and it has proven itself in dozens and dozens of installations over the years to deliver very high results. Just one quick mention about some of the logistics about how it works. So it is a cloud-based system that is running all these algorithms. It has this digital twin that is taking all the data that we're feeding in, and it's identifying in real time new set points. It may be a DO set point, it may be blower operating speed set point. It may be a pump flow rate set point. Just depends on what the full range of solutions that have been implemented are, and it automatically loads those into the new PLC on a real-time basis. It includes, there's a user interface that has different levels for operators, for engineers, for plant managers and oversight staff to view various KPIs and can see the big picture or see the very small drilled down picture as appropriate for the individual that is operating or using the system. Louis also mentioned it's been developed over a wide range of time. We've been doing this since the 90s, and it was implemented at that time on a server located at the plant. Obviously, there was no cloud component at that point in time, but it has been cloudified within the last 5 years. And what that does is it actually makes it much more efficient. It's less costly. And it makes it easier to take advantage of updates, as they can very easily and simply be downloaded. So you always have the latest and greatest information, the newest version of the algorithms that are running and optimizing the various unit operations. The results that we've seen, just in general, we see an average of 10 to 30% lower aeration energy when we're employing it in a secondary treatment system, 25 to 75% pumping and mixing energy reduction. There is grit separation specific modules and have seen improved separation with a big reduction in energy on the grit chamber aeration. Very significant chemical savings, less sludge production because we're feeding less chemical to achieve the same types of effluent phosphorus and effluent total nitrogen. There are anaerobic digestion specific modules that improve gas production. And all of these work together in any facility to produce better effluent concentrations and better compliance overall. We also see significant increases in capacity, and we have implemented the solution specifically in many instances to achieve these types of capacity increases. These being the primary drivers on a project to say avoid building an additional treatment train or avoid building an additional secondary clarifier. So once you have the right data and you have the right algorithms, which we do, which we've tuned over many, many years, and we've done that from a wastewater perspective. We are at our heart, we're a wastewater company. We're not a data science company, although we certainly employ some data scientists to work on this particular product. But we're coming at it from a wastewater perspective and have done so in building these algorithms. So when we have the right data, we can affect some very significant change and improvements in these facilities. And all this leads to some additional benefits beyond just what you see in numbers in terms of chemical consumption and improved capacity and those kind of things. The better compliance, more stability, better overall settling, and staff advantages, and being able to track and monitor performance better, at the big picture, at the management level. The best reference or the best tool for us is our customers, and we're always willing to get our prospective customers in contact with our clients, to existing users to talk about their experience. We have I think a great track record with that. So enough about that. I think we're going to move into some more detail here. This just summarizes really kind of the heart, a lot of the key modules. I'm not going to go through these one by one. I'm just going to pick out a couple examples, and then we'll talk in specifics about the results at the Kruger plant and what they implemented. But you can see there are modules that have been in place for many years that continue to grow and that all work together to optimize a plant. Again, a particular facility, depending on the objectives, just one or two of these may make some sense to implement. A dozen or more may make sense to implement. The more you implement, the more it will build on each other and better optimize the facility as a whole, and also out into the collection system, and really treat the collection system and the plant as a single, kind of entity, and optimize that all at once. So I want to give one example of a common approach to where we affect change. So, there's a stormwater control module, and there's different levels of that. It can be very simple, and it can get more and more elaborate, and it all depends on the data that you have available. If you have a system and you have a certain flow capacity, say before your clarifier is going to wash out, that probably is what it is. And ATS here means aeration tank settling. A common method that some plants use is just to manually, if they know they're going to get washout, they'll turn off the aeration in one or more of their aeration tanks, build up some solids there, reduce the solids loading on the clarifiers, and that helps. That requires manual intervention and can certainly be managed better and can be automated. So if you've got a plant and these are your actual flows, this whole period here above that dotted line represents potential clarifier washout time, right? Well, you implement aeration tank settling, you can head off and avoid that. But the problem is you might not implement it in time. If you're manually implementing it, or even if you're automatically implementing it, say just off of a flow signal at the plant, there's going to be this period of time potentially as you're transitioning aeration tanks to settling where you're still susceptible to some washout. So the question is, how can we better anticipate the flows actually at the plant? And there's a variety of ways that we can affect that, and they just get more and more fine-tuned depending on the type of data we have. So there are proven algorithms that we build in with our flow forecast that go along with the stormwater control mode that take data from rain gauges out in the collection system, from weather APIs to build forecast data in, and use those to identify when's the right time to implement some aeration tank settling, and do so fully automatically, and help that facility weather the storm, so to speak, and minimize risk of washout. Again, that's been perfected over many years and works exceptionally well, and takes some of that burden off of the plant to try to figure out when to start implementing things. It can just go and do it on its own. So that's one example of how we're utilizing digital technology and these advanced algorithms to improve what's happening at the plant based on better data. We're going to get in a little bit more detail. I'm going to turn it back over to Louis to talk about specifically phosphorus removal and what we're doing with that, and the solution ultimately that was implemented to affect change at the Kruger facility. And then we'll wrap it up with looking at some actual numbers from that plant.
Thanks a lot, Mark. Yeah, so we just looked at the stormwater, and as we mentioned earlier, so all these modules and algorithms, they can work together. So the plant can always, the idea is to adapt the plant to any kind of situation that's in. You're going to have fluctuating flows throughout the day, throughout the year, with different contexts. So how to best adapt the process to the state it's in and maximize the use of the concrete and what you have your asset there. So a focus on biological phosphorus removal here is that we know that during a day, most probably there's going to be fluctuations in the plant, and we want to look for times where we can enhance the biological P removal in existing volumes. The idea is not to build more, it's to use it smarter, wiser. And so that's the why in it. So, and how do you do that? Well, we try to find time slots and periods of time, usually during the low load time frames, for example, during the night, where your plant is going to be operating below capacity. So you're going to have some spare biological capacity somewhere in there. And essentially, by tracking this in real time with ammonium and nitrate and flow measurements in real time, we can say, fine, now is the time to introduce anaerobic volumes and zones in the concrete tanks that are already built. So instead of just using an anoxic tank for a denitrification phase, we'll be using it to create anaerobic conditions where the biop bacteria are going to be able to feed on the incoming COD and grow their capacity of impact on the process at a later stage, so that we're giving them priority in the feeding chain to be in best conditions and then perform best at a later time without impacting the effluent quality. Because by introducing these times in low load situations, we're doing it when we know that we have the spare capacity in the rest of the volumes to do the necessary treatment and reach the compliant levels in the effluent. And so this is a patented solution within AQUAVISTA Plant, and it's applicable to all activated sludge plant designs. So we're giving you 3 of the main ones at the bottom of the screen here. So the biodinitro that Mark introduced earlier. So here with the introduction of where we're prolonging the phase, the anoxic phase into an anaerobic phase, so essentially waiting for all the nitrate to be gone and have no DO and no nitrates. Same goes for the single ditch activated sludge as in it setup, where we just change the process to prolong these anoxic phases. And finally, in your conventional recirculation plants, plug flows, what we'll do is that we'll stop the internal recirculation within the line. You'll see with the little crossed X on the orange line there, so that we don't return any nitrates from the end of the tank to the beginning where we want to create anaerobic tanks. So we'll have dedicated anoxic tanks in the beginning where we don't recirculate anything. And then you have your anaerobic conditions for your biop growth. And so that's kind of how we in live work on this stuff. But it's not only one thing that makes the biop process possible. When you could think of AQUAVISTA Plant somewhat like making the orchestra of your asset to play in tune the best way, to play the partition correctly. So all the algorithms together are going to be better if they act according to each other and according to what the process needs. So on the top right part of your smart biop wheel that you have here, you have the DONN removal, which is the algorithm that controls the aeration and the DOs in your aeration tanks. So that's the one that's the algorithm that's going to think and tell, let's stop aerating now to create these anoxic and prolonged into anaerobic conditions. But if you also have mixers in there, in your anoxic zone, you might have a second algorithm and a second feature adding on top of it as an additional benefit to stop the mixers, to increase the hydrolysis rate. So you'll have an increased hydrolysis rate and you'll be doing savings on your energy by not running your mixers. Ultimately, also, all your process is based on how much bacteria do you have in there, how are you going to do it. So that's your solids retention time and your return activated sludge. You want to make sure that you have the right sludge age and the right sludge amount in your tanks to do the biop removal, to reach your compliance in the effluent, and not have to over aerate by having too much sludge in the system. An algorithm like that will make sure that you have the right balance in between those 3. Same with the return activated sludge. So how much are you pumping back? Because sometimes you don't want to be creating unnecessary constraints on the system by returning too much. So here you can say that you could increase the hydrolysis at the bottom of the settlers by minimizing the return rate. In our recirculation plants, as I showed before, you have your internal recirculation, your nitrate recirculations. Well, you need that extra feature to play together with the DO&N removal feature in a recirculation plant to make sure that you can achieve this anaerobic condition in the beginning of your aeration tank. The two final ones in the wheel here you have, there's another patented feature is standby, is essentially when your plant, if you have a plant that sometimes is operating far below its design capacity, you might actually be able to just do the job on half the lines. If you have 2 lines, you could maybe just do it with 1 and save a lot of time of operation for aeration and mixing. But essentially also, if you can put a separate line in total standby, in pause for a couple of hours, that is always dynamically in real time able to come back into operation if the load to the plant requires that, well, you're creating one huge anaerobic volume for your plant to prepare for for the process at a later stage. And this done dynamically. So it can be one line, it can be the other, it can be for just an hour, it can be up to 4, 5, 6 if needed, always dynamically ready to come back into operation. And finally, if the whole BioP process can't take it all, where you're gonna have to dose something. And let's just make sure you don't overdose by having a P precipitation algorithm telling your pump, well, now we need to dose this much. Not too little, not too much. So it's all well and nice. We've kind of gone through the logic behind how we provide this optimization. How do you make it possible? What did it look like in reality for the Kruger plant here? So as Mark said, it's about 100,000 PE, and they were really struggling with 3 main things that I'll repeat to you guys. So first of all, in Denmark, you have to provide operational savings reductions every year. So that's the requirement for the government. So every year you have to think of a smart way to save a couple bucks. That was one of the issues. The second one is that, as Mark said, they were struggling with the sludge escape from their secondary settlement. And not only were they struggling with the secondary settling tanks during stormwater events, they were handling it manually, everything. So the guys at the plant were actually sometimes needed to wake up at 4 in the morning and get to the plant and all hands on deck to try and get the plant through this stormwater event. Denmark's a very rainy country, so really when it rains, it pours. So this was also a strain on the operational team, that every time there was rain, they needed to come to the plant and make the best of whatever they could there. So those were really the 3 main drivers at the beginning. And by using 9 of the different features, some of which are the ones that we showed you before, so DO&N removal, and solids retention time, and return activated sludge, and P precipitation, for example. Those are a couple of them. Stormwater, of course. They were able to so we replaced the existing real-time control that they had implemented, which was delivering just very little OPEX savings. That was pretty much what they had achieved with that. We actually managed to introduce one BioP removal in a plant that did not have BioP concrete tanks or anaerobic selectors. And that resulted in 60% reduction of the chemicals used at the plant. So quite a significant impact on the OPEX line, since they had to buy much less chemicals. With the setup of a stormwater algorithm, the plant was actually able to increase its flow during stormwater events by 100%. So they were able to handle more water and automatically. The guys didn't need to show up at the plant anymore because the tool was doing it for them. It was sending the set points to the PLC carrying it out and handling the event by itself, securing the sludge blanket levels at a level that did not put them at risk for any sludge escape, and ultimately result in a much easier operation of the plant. Finally, in times where there were no stormwater event for the rest. The DONN feature, along with the rest of the features, managed to provide 25% savings in the aeration tanks on top of what had already been achieved before with an existing real-time control. So this is really impressive results, and we have a very good relation with the customer that has been using this for quite some time now and is building up on the tool. So they've implemented 9 features to begin with, but actually recently they bought 2 more features. And since this is a cloud solution, it's very easy for them to add, as we've just created their plant as a digital twin in the cloud. So it's at a minimal cost whenever you want to extend the level of optimization. That's good for your plant.
Thank you very much, Louis. I think that's a very compelling story there at AQUAVISTA, and I do want to make the point those types of results are pretty typical with what we see. You know, it's not a you know, a once in a lifetime kind of result. It's we see these results over and over again in the facilities where we implement the solution. You also mentioned
Mark, I wanted to add that here we've given you guys an example of a plant that's 100,000 PE, but we have references ranging from, I think one of our smallest is 2,000 PE, maybe 5,000, and our largest reference is 2 million PE, and the largest plant in Poland it is. So these results are achievable on plants of all ranges, and not just dedicated to this kind of setup.
Absolutely, yeah. And you had also mentioned, you know, being in the cloud, the ease of delivering added value through additional modules, additional algorithms being implemented, you know, down the road. They're adding a couple new ones. I want to wrap this up with just one final thing. You know, one of the ways that we do that, and they haven't implemented this at that Krueger facility, but we have what's called AQUAVISTA Lab, and this is actually sort of a collaborative platform that allows our AQUAVISTA Plant customers, if they choose this option, to work on and develop their own algorithms, and we can essentially partner up to identify new ways to set up advanced control and in the digital twin environment that's created in the software, be able to fully test it and confirm how that's going to work. And that is I think a very neat feature to add some value on top of what's already generated and what we're generating as time goes by. So just wanted to make one final mention of that. And so at this point, I'm going to go ahead and finish the presentation part, and we'll move on and see what we might have for questions.
Okay, thank you, Mark, and thank you, Louis. It looks like we do have time for some questions, and I've gotten a few. First, is there any study or report that shows the optimization results in terms of dollars saved by wastewater treated?
A report that puts it into dollar values. Louis, I will defer to you on that. Do you guys have any, whether it is internal or a third-party consultant or you know, a paper presented at IWA or something that takes the savings percents, you know, that we see and for a given facility, you know, just sort of generalizes and breaks those down and puts those on a euro or other currency, you know, basis.
So just for me to be sure that I understood the question, is that the percentages that we presented here, were they translated from something that was a euro value, or what's the usual range of how much this represents?
So yeah, I can't read too much into the full context of the question necessarily, but I think what it's asking is if we you know, can have, you know, sort of quantified, you know, like dollars per cubic meter per day savings, you know, something on a general, real financial basis as opposed to like just actual percent energy or percent chemical. I mean, it will depend on energy rates, it will depend on chemical rates, and those vary from place to place. But do you know of any reports you have that really actually focus in on dollars or euros?
Yeah. So that we can estimate it on a case-by-case basis in two different ways. So one, it's either in a phase where we're looking into the plant at the beginning and see what's the potential for optimization here. We'll both look at the potential for optimization, saying we'll reach 15%, and how much in euros or dollars is that going to translate into by correlating it with the according cost of electricity and cost of chemicals for each plant. So even when you don't have the tool, but you're looking into the possibility of getting it, we'll try and calculate those two. Once you have the tool to know how much are actually savings here, in the KPI, in the manager overview user interface, there is a live calculation of your kilowatt hours per cubic meter treated. So you can essentially compare how much the efficiency from before and after implementing the tool, and then making the difference between both, you can estimate how much more efficient you are, and thus how much you've saved on it. The same can be applied to the number of, for example, liters of chemicals that you've put into this. It gets a bit more tricky when it's a bit more, let's say, environmental economics side. So how much do you save from being compliant more of the time, or saving in man hours that do not have to focus on doing manual stuff at the plant, or even handling better stormwater events if you don't have taxes or penalties when you have sludge escapes. Then it becomes a bit more difficult to put a dollar value on it.
Right, yep.
Okay, thank you guys. Next question. How do design engineers justify the increase in organic and hydraulic capacities to regulators who review designs based on design standards such as 10 state standards?
Yeah, that is a good question, and I think that will vary from state to state here when we are looking at new facilities. In terms of the capacity increases we're talking about, at this point, it's probably more, it's less about actually re-rating a facility, say, and it's not generally changing our design approach and how we work with consulting engineers in developing the design on a new facility, say. So generally for us, the capacity increases, like I said, they're more about better managing washout, better managing things in an existing plant, and not so much about re-rating it and working through things with regulators. But I am certain that will come up. We haven't approached that here in the U.S. yet, but I do think that the time will come, and it will just be something to handle on a case-by-case basis, and it will rely on a couple factors, actual modeling of the facility, and accounting for, with that modeling, having advanced control, and this type of this system included, and then showing real world results, which we certainly have an abundance of data on that.
Okay, thank you. Next question, is this software run by Veolia, or can it be downloaded and run by the design engineers or plant operators?
So it is a proprietary software that runs on our servers and is delivered through the cloud. So it's not a software package that we that we give to engineers or customers. So the treatment facility, the utility, the plant, they're making use of it, but the software is all running back on our servers and is delivered through the cloud.
And I think an important point here is the tool is once implemented, handed over to the user and to the team at the plant entirely, with a dedicated, tailored training in how to use and make the best of the tool. So the teams at the plant will really feel that it's their own. It's a tool of their own, and not only handled solely by Veolia. It's a very collaborative thing where we as Veolia help in the implementation and make sure that it's best used by the guys who are actually there.
Okay. Next question. What nutrient analyzers do you use?
So when it comes to process control, we are, our experience, which is pretty vast, is really pointed toward a need to use wet chemistry analyzers. And our, when we're talking about the DO and N module in a plant, say that's doing total nitrogen removal, we utilize both ammonia and nitrate continuously in the algorithm, and we use wet chemistry analyzers for those. What we found with, particular with ion selective probes, the level of drift that they have and the need to keep them very well calibrated leads to inoptimal control. So, we've used analyzers from a variety of different suppliers. We do use a lot of HOC products. We use a lot of ASA products with the ChemScan analyzer. We've used Anderson-Hauser analyzers. So, one thing about our system is we are analyzer, we are manufacturer agnostic from that point. So, implementing AQUAVISTA Plant, you're not locked into one particular supplier from that standpoint. So if you really like HOC stuff and you want this implemented with HOC Amtax and Nitrotax, absolutely, we're on board with that. If you love ASA stuff and you want to implement with ChemScan, absolutely, we're on board with that. But again, we do have guidelines as far as wet chemistry analyzers and not probes. Depending on the function, there are some modules where maybe a UV nitrate probe might make sense. But predominantly we're analyzers. Louis, I don't know if you had anything else you wanted to add to that.
No, I think that's yeah, that was the point. Is whatever's already there at the plant, we can use it, and completely technology agnostic. Whatever you want to implement, we can help and give some guidelines. Wet chemistry is a preference for us, but it's completely up to you, and we're happy to help you out with our experience and what we've had good experience with.
Mm-hmm. And the last thing I will mention with that, so we will implement the solution. We can include, if you don't already have the instrumentation needed to implement one or more of the particular modules that are of most benefit to you, we can offer the system with us including the instrumentation. We're fine offering a system with you procuring that on your own. The instruments don't have to come through us. We do have, I think, very, very good pricing with the number of instruments as a global organization that we purchase. And sometimes I think we can deliver those at a lower cost to the end user than they can actually get them buying them themselves. But from that standpoint, it's whatever works best for you, whatever works best for the plant, we can work with.
Okay, thanks again, guys. It looks like we're just about out of time, so thanks to the presenters for today's webinar. Those of you in the audience will receive a recording of today's webinar and a follow-up email with instructions on how to reach out to our presenters with more questions. Any questions we didn't get to today will be answered in a follow-up email. Thank you all for joining us today, and that concludes our webinar.